Hi, in this video, we want to take a look at fractional factorial designs. Okay, so in full factorial designs, we're going to go through and we're going to collect data on all possible combinations of all of our variables. All right, now this is the ideal. This is what we want to have. We want to have full factorial designs, but there's a problem that the number of data points I need to collect can get out of hand very quickly with full factorial designs. So if I have a lot of variables or my variables have a lot of levels, it can just be impossible to get all the possible combinations. So what we're going to do is we're going to do a little bit of mathematics, and it's actually abstract algebra, and we're going to take our full factorial design. We're going to do a homomorphism from group theory, and then we're going to get a subset of our rows that we want, and then we're going to start collecting our data. So also something I need to point out is in experimental design, everything we're talking about is before we collect our data. And so what we're doing, we're trying to set it up so that we can get as much information out of our data as possible. I want as much bang for my buck for the data that I collect. So I'm setting up a game plan to make sure that mathematically I have as powerful of data as I can get. All right, so what we would like to do is have all possible combinations of our predictor variables. That's not possible. Either we don't have the money, we don't have the time, we don't have the patience, we don't have the resources, whatever it is, for some reason, I can't do all of them. So I'm going to do a fraction of the possible runs. Okay. And so that's where the word fractional factorial design comes from. All right, so kind of bring this to make this a little bit more clear, let's look at a poorly designed experiment. All right, so check out the situation. So what I'm going to do is I'm going to go out, I'm going to collect data, I'm going to look at the response variable. I'm going to look at the dependent variable, and I want to do a linear regression model where that response is the target variable. Okay, and my predictor variables for this linear model is going to be sex, side, and treatment. Now I'm going to go out, I'm going to collect data from men and women. I'm going to have treatment on the left and the right side, and I'm going to have two levels of treatment, high and low. Now, this is a very poorly designed experiment because you'll notice that sex, side, and treatment, if I have male, I always have left, I always have high. If I have female, I always have right, I always have low. And so there's no way for me to tell that is the effect that I'm looking at. Is that from sex? Is that from side? Is it from treatment? Is it from a combination of them? I don't know. I can't pull it out of the data. Now, poorly designed experiments are better than no experiments. So we can do data science. It's better to have a poor experiment than no experiment. But in the design of experiments phase, there's no reason why we wouldn't make this better. So let's make this a little bit better. So now we're going to improve it. We're not going to fix all the problems, but we're going to make it a little bit better. All right, so now you'll notice that I've shuffled male and female by the left side and treatment alone. So when I look through this, okay, so I'll be able to tell if its sex is linearly important in the model, but side and treatment, I won't be able to parse those out. So there's no way for me to figure out, is it side, is it treatment, is it a mixture of the two from the data I'm about to get. So this is better, but we can do even better than this. So let's go ahead and improve it all the way. So now you'll notice I have sex as I go down, I alternate male, female, male, female, male, female. So after each time of one, I switch. Now with side, I go left twice, switch, right twice, switch, left twice, switch. And then I have treatment. I go high 4 times, and then I switch 4 times. Now, if I had another variable, it would be on the next one, I would do 8 times and then switch. And so this is a way for us to generate a full factorial, is that the first column alternate like a pattern of 1, and then on the next column, like length 2, then switch, length 2, switch, and then here on the third, length 4, then I do 4, switch, 4 switch, 4 switch, and then the next one will be do 8, then switch, 8, then switch, and keep on going all the way down. And that'll give us all possible combinations. If I look through here, I have all 8 possible combinations of sex, side, and treatment. So this is a good, well-designed study. And this sets it up so that with as little data collection as possible, I'll get as much information as possible. All right, so now let's go ahead and convert this over to plus and minus ones. Now, the reason why I'm going to do this is because this sets it up so that I can actually start invoking some abstract algebra to make to do that homomorphism mapping and get a better subset of rows when I'm not able to do all 8. All right, so what I'm going to do, I'm going to replace each of the levels with plus or minus 1. All right, so sex is 1 or minus 1, side is 1 or minus 1, treatment is 1 or minus 1. Now, when I have a numeric variable, so let's say that treatment is like a dose and the amount that's being given. And so here, for a factorial design, what we'll do is that we won't look at all possible values for our numeric variable. We'll look at a high but reasonable value for the high level and a low but reasonable value for the low level. And we're going to go as far, we want to spread them out. And in fact, this will actually do better for our linear regression model. Intuitively, most people would think go through and like set up a grid of numeric values. Well, there's a disadvantage to that in that when I do my linear regression, the coefficients standard error will be less if I increase the variance of the x variable, of the predictor variable. And so actually from that point of view, from a hypothesis testing point of view, we like this high-low scheme. All right. So now I've got this set up for my design. Let's consider the interactions. Well, the interactions, what I'm going to do is I'm going to multiply together. So I'm going to add the intercept onto my design matrix. I'm going to, for the two-way interactions, I'm going to multiply the 2 columns together. So for sex side interaction, I take sex times side. For sex treatment interaction, I take sex times treatment. For side treatment interaction, I go side times treatment. So this gives me all of my 2-way interactions. And then for the 3-way, I just multiply all 3 together. Okay, and so now I'm just, this next step, I'm just reordering the columns. And so now you'll notice that my predictor variables form an 8x8 square matrix. And take a moment, check this out. Notice that if I add any of the plus minus ones columns, if I add all of them up, I'll notice that they're all adding up to 0. So you'll notice that the intercept column is orthogonal to all of the other predictor columns. In fact, if I go through and I do the dot product between any 2 predictor variable columns, I'm going to see that I have 0 as a dot product every time. So what this is saying is that in a linear algebra point of view, is that each one of my predictor variable columns are giving me completely distinct information. There's no overlap. Contrast this with the idea of, let's say that I have 2 independent variables, 2 predictor variables. One is height, one is shoe size. All right, height and shoe size are correlated with each other. They're not exactly the same. They're not perfectly correlated with each other, but they are correlated with each other. So if I have height in my model, it's highly likely that shoe size is going to be redundant. If I have shoe size in my model, it's highly likely that height is going to be redundant also. In this full factorial design that we're looking at right now, there is no redundancy at all. There is no overlap. Everything is completely distinct. Also, if I look at that 8x8 matrix, it's an invertible matrix, which means that I'm maximizing the amount of information that I can get from such a small number of rows of data. All right, so now let's actually do a factorial design. All right, so when I only have two levels, when it's a two-level factorial design, if I want to do a fractional factorial design, what I want to do is just set one of the columns equal to a constant. All right, so what I'm going to do is I'm going to restrict all the rows of data to a one particular value in that column. So here you'll notice that I'm taking the three-way intercept, and I'm going to restrict my rows only to the case where the three-way interaction is equal to 1. Now, I could do 1 or -1. I chose 1 because it's a little bit easier to see a point that I'm going to be driving at in a moment, but it'll work out either way. Okay, so now I want you to take a look at this. Look at the intercept column. Look at the three-way interaction. You'll notice that they have perfect correlation with each other. In fact, they're actually equal to each other, but if I would have had -1 here, they would have had perfect correlation. They would have had opposite signs. But, okay, so after I set this to a -1, this would have been all negative ones and would have had perfect correlation with the intercepts. They would have been negatives of each other. All right, so now check out sex and side treatments. You'll notice sex and side treatments are perfectly correlated with each other. Check out side and sex treatments. You'll notice they're perfectly correlated with each other. You'll check out treatments and sex side. They're perfectly correlated with each other. All right, so what has happened is up here, this is the situation I want to be in. This is what I want. This is what I like, because I'm getting as much power from my data as possible. I can study the main effects, the two-way interactions, and the three-way interactions off of 8 data points. That's the least amount of data that I could possibly have to achieve so many interactions. Now, when I get down to here, it's impossible for me to statistically tell if the impact of what I'm seeing is coming from the intercept or sex side treatment. It's impossible for me to distinguish sex from side treatment interaction. It's impossible for me to distinguish side from sex treatment from a statistics point of view. It's impossible to use the data to distinguish between treatment and sex side. So when I get my output, I have two choices on this. When I run my analysis, either I have to ignore one of the columns from each of the pairs in my analysis, or I can go take a look at what I get and then do subsequent studies to go deeper into particular values, depending on what's going on. So if I had data for 6 possible runs of experiments, and I'm trying to maximize for the purpose of the study, maximize the response or minimize the response, I'll look at what's going on. I'll find the level that has the maximum value, and then I will start looking at, trying to distinguish between pairs after that. And so here, it's impossible for us to tell statistically what's going on for these two. That, from the homomorphism mapping, these have been squished together, and I can't separate these two. I can't separate sex from side treatment using the data. I can't separate the information from side and sex treatment, and so on. So fractional factorial designs are really our best choice when we wish that we could do all possible combinations, but we can't. So we've got a pretty powerful setup. And one thing that's nice about, the theory that's already been done is that before I launch my experiment, I can actually know, like, how much of an information loss am I suffering? What are the shortcomings of my design? Because if I just want to look it up and look at like the help documentation, in the FRF2 package does a pretty good job of explaining, the different strengths and weaknesses of what you're doing. All right, so the fractional factorial designs using R, we have several packages. So in design of experiments, R absolutely dominates design of experiments. There is nothing that even comes close to the features and the power and the utility for design of experiments. And so the one that is the big heavy hitter for us is going to be FRF2. All right, so this is focused primarily on two-level designs, but can also handle mixed levels. And so when we build our experiments, we're going to have to say the number of factors, and we're going to need to say what our resolution is. All right, so resolution 3 confounds the main effects with two factor interactions, and resolution 4 confounds main effects with three factor interactions. And a resolution of greater than 4 are usually considered pretty strong. And so if I want my design, I just say factors and resolution. There are other parameters that we can put in there for the function, but I wanted us to just focus on these main two to emphasize, the conversion from full factorial to fractional factorial. So here's resolution 3 with 5 factors. Resolution 4 ends up being is 16. Resolution 5 is also 16. Now, something that's interesting on this next one, when I do resolution 6, when I have 5 factors, we end up having a full factorial design. So if I keep on increasing the resolution, eventually I'm going to get full factorial design. All right, so now for the homework problems, what you're going to do, you're going to take the data set that's in the DOE base package and go restrict it to just the two-level predictor variables and the target variable of biomass. And you're going to go in, do linear models, and I want you to have hands-on experience, just looking at these data sets, look at the difference between each of these levels, and then I want you to do linear models, and I want you to take a look and see, what's the difference in these models. All right, well, that's all I've got for you. Life is short. Do math.